just as we make a table for a 5-hour clock, we can make a table for a 6-hour clock. We can actually make tables, multiplication and division tables. A 6-hour clock is going to look like this, and all the principles that we used with the 5-hour clock are going to relate to a 6-hour clock. Now I suggest that before you watch the rest of this clip, you pause and actually construct a 6-hour clock instead of watching me construct it, because I'm not going to construct it in all the detail I did with a 5-hour clock. Hopefully you've paused and constructed your own multiplication and addition tables for the 6-hour clock. The addition table I'm going to write down without too much comment because it's very similar in nature to the addition table for a 5-hour clock. The only difference is that on a 6-hour clock you've got a 6th hour, but the patterns are all very similar. 1 and 0. Well, the 0 is going to always give us the same numbers that we have in our table. Very important property, called the identity property, incidentally, and we'll formalize the meanings of those properties shortly. Then the tables are just going to go sequentially. Up to 5 and then back to 0 because of the way the clock works. So there's a table for addition mod 6. Has all the characteristics of the table for addition mod 5. We see the row of zeros moving backward each time. We see all the sequences. We see the columns that repeat the table. All that occurs here too. The zeros marching to the left, the numbers increasing by 1 each time you go down the column or go from row to row. So that's not really a very interesting table in a lot of ways. Once we see how the addition works, it's always the same. Or it always has the same nature on every clock. Multiplication is a little bit more interesting. If you've done this, you probably noticed that there are some differences between the nature of this table and the nature of the table for the 5-hour clock. And I can't seem to write my numbers down correctly here. This is supposed to be a 5. Okay, on a 6-hour clock, we do certainly have some things in common with the 5-hour clock. One is that if you multiply by 0, you're going to get 0. Because again, if you go so many hours 0 times, you just don't go anywhere. So that we can easily fill in the first row and also the first column of this table. Also, if we multiply by 1, we always get the same thing. That applies to clocks as well as to numbers in general. So there's nothing new here. Now let's see what happens in the remaining rows. Okay, in row 2, 2 times 2 is 4. Well, that stays on the clock, so we've got 4. 2 times 3 is 6, which gives us 0 on a 6-hour clock. It gave us 1 on the 5-hour clock. And 2 times 4 is 8, which is 2 on a 6-hour clock. 2 times 5 is 10, which is 4 on a 6-hour clock. Now something has happened in this row that didn't happen before, and I'll leave it to you to think what that might be. I'm going to go ahead and fill in the column here. 3 times 2 is 6, which is 0 on the 6-hour clock. 4 times 2 is 8, which is 2 on the 6-hour clock. 5 times 2 is 10, which is 4 on the 6-hour clock. Those are the same numbers that we got here. The 6, 8, and 10 are the same, leaving us remainders of 0, 2, and 4, here as well as here, showing how the multiplication is commutative. It doesn't matter in which order we multiply, we get the same result, and that makes the row the same as the corresponding column. That is, the row across from 2 is the same as the column leading down from 2. If we continue the table, 3 times 3 is 9, which is a remainder of 3 on a 6-hour clock. 3 times 4 is 12, which is 0 on a 6-hour clock. 3 times 5 is 15, which is again a remainder of 3. 4 times 3 is 12, which is a remainder of 0. Well, of course, because of the commutativity, we're going to get the same numbers here that we got here. Okay, now the row across from 4. 4 times 4, we have all the numbers up to this one, but 4 times 4 is 16, which is 4 on a 4-hour clock. 4 times 5 is 20, which is 2 remainder when we divide by 6. Okay, 5 times 4, of course, is 20 again, leaving us the same remainder. 5 times 5 is 25, which leaves us a remainder of 1 on the 6-hour clock. Now, what has happened in this table that didn't happen in the table for multiplication on the 5-hour clock? Or, maybe better, what did happen on the 5 that didn't happen on the 6? Well, whichever way you look at it, we see that there are repeated numbers in most of these rows, at least in the rows for 2, 3, and 4. Whereas on the 5-hour clock, there were no repeated numbers in any of the rows, and since columns are the same as the rows, there are no repeated numbers in any of the columns. Another thing we noted, of course, was that every number appeared in every row and in every column, and that certainly isn't the case here. We only have 0s, 2s, and 4s in the row across from 2 or the row across from 4, and only 0s and 3s in the row involving the 3. You might think about why that happens in terms of the way the numbers behave and the way the remainders behave on a 6-hour clock as opposed to a 5-hour clock. We'll use these tables to identify a couple of important properties that operations can have. In the first place, addition or multiplication on a 6-hour clock is closed, meaning we only get we can only get a 0, 1, 2, 3, 4, or 5. The numbers in our original set are the numbers that we get. We can't get anything that doesn't appear on the clock. There's an identity. An identity is an element that doesn't change things. We see that if we combine a 0 with anything on an addition clock, we're going to get the same thing back. 0 doesn't change things. 0 doesn't change where we are on the clock. So for addition, the identity is 0. For multiplication, the identity, the thing that doesn't change what we combine it with, is of course 1. Okay, so identity doesn't change things. On the 6-hour multiplication clock, it's the 1 that doesn't change the numbers that it acts with. And the 1 here doesn't change the numbers over here. So 0 for addition is our identity. And 1 for multiplication. Another important property is inverses. Inverses are numbers that we combine to get the identity. In the case of the addition table, the identity is 0. 0 and 0 give us 0. 1 and 5 give us 0. 2 and 4 give us 0. 3 and 3 give us 0. Of course, 4 and 2 and 5 and 1 also give us 0. The pairs 0, 0, 1, 5, 2, 4, 3, 3 for addition. If everybody has an inverse, if every number appears as an inverse, then the table's said to have the inverse property. Now, this table, the table for multiplication mod 6, does not have inverses. Some numbers do. 1 and 1 will give us 1. 5 and 5 will give us 1. So for multiplication, those are our inverses. 5 and 5, 1 and 1 are the inverses for multiplication. But other numbers don't have inverses, so that the multiplication table does not have the inverse property. 2 doesn't have an inverse. You can't get 1, the identity, for multiplication if you use 2. We'll see some other properties, some important properties on the next clip, but we wanted to introduce these in terms of some of these tables.